So, grüß Gott, meine Damen, meine Herren. Ich freue mich sehr, hier wieder sehr zahlreiches Publikum zum EDA-Workshop begrüßen zu können. Wir hatten ja 2 virtuelle Jahre, 2020, 2021. Letztes Jahr sind wir ja dann schon in den Präsenzmodus zurückgekehrt, Ende Juni in Dresden. Da sah es noch ein bisschen anders aus, da haben wir noch diverse Masken gesehen und einige Teilnehmer haben sich eine obskure Krankheit eingefangen. Jetzt sind wir, glaube ich, wirklich wieder zurück in der Normalität und es fühlt sich natürlich auch sehr, sehr gut an, wieder miteinander interagieren zu können. Also herzlich willkommen zum EDA-Workshop und viele von Ihnen werden dann ja auch am Mittwoch noch zum Tag der vertrauenswürdigen Elektronik bleiben. Der EDA-Workshop dient ja vor allem auch dem Austausch zwischen Industrie und Forschung. Das ist, glaube ich, so einer mit unserem Markenkern, dass wir eine wunderschöne Balance haben zwischen Personen aus der Forschung, Personen aus der Industrie. Wir haben morgen dann ja auch die bekannte und bewährte Posterausstellung, wo wir zum einen verschiedene Poster aus Projekten heraus vorstellen und zum Zweiten auch das Konzept, EDA-Professoren stellen sich vor, wieder aufgenommen haben. Das hatten wir vor ca. 10 Jahren schon mal gemacht. War dann etwas in Vergessenheit geraten. Wir werden dann ja morgen auch sehen, auch da zeigt sich, Deutschland wird etwas internationaler. Da stellen sich einige dann auch auf Englisch vor, weil aus dem Ausland Professoren zu uns nach Deutschland gekommen sind, was natürlich eine wunderschöne Bereicherung ist. So, und heute, ich denke, wir haben 2 Tage ein sehr spannendes Programm, hoffentlich auch interaktiv, liegt natürlich an Ihnen allen. Und jetzt beginnen wir direkt mit der ersten Keynote. And for this, let me switch to English. The 2 keynotes will be given by international speakers. And today we have, I'm very honored that we have Professor Onur Mutlu with us from ETH Zurich. He has a very distinguished career. He is one of those people who have tremendous academic impact, but still have very significant industrial background. He currently is a professor of computer science at ETH Zurich, and also still is a faculty member at Carnegie Mellon University in the US, where he previously held the Strecker Early Career Professorship. His research interests are in computer architecture, systems, hardware security, and bioinformatics. His research has really had very, very much insight. He has had industrial, very distinguished positions. He started the computer architecture group at Microsoft Research about 15 years ago, and then had positions at Intel, AMD, VMware, and Google. He has a super huge list of awards, which are all well deserved. Let me just mention he's an ATL fellow, he's an IEEE fellow, and a member of the Academia Europaea. And I don't want to take any more time from you. Only great to have you here.
Thank you very much, and thanks for coming. Okay, looks like this is working. That's great. Thank you. It's a pleasure to be here. It's my first time in Hanover. It's a beautiful city. And it's a beautiful day. So if you're bored, you know where to look. Hopefully this will not be that boring. So I'm going to talk about memory-centric computing. This is an area that I think is fascinating today. And this is something that we had to do, in my opinion, to fundamentally make our systems much more efficient and much more higher performance and much more sustainable all at the same time. But of course, it's not easy to change the paradigm from compute-centric to memory-centric. So I'm going to do some motivation and then give you some examples. I have a lot of slides. We will not be able to cover everything. I already figured out that I got the date wrong because I gave the same talk 5 days ago, but we replaced that 3 with 8 today. Okay, so if you look at computing today, computing is bounded by data. And data is really key for many, many applications. Machine learning, genomics, databases, all the important workloads are data intensive. They require rapid and efficient processing of large amounts of data. And they require increasingly sophisticated things to be done on the data. And on top of this, data is increasing. It's actually exploding. And we can generate much more data than we can process in many domains. I'll give you an example domain from genomics soon. But clearly, everybody knows about machine learning, and machine learning computation and memory requirements are both exponentially growing. And this is a beautiful talk by the CTO of this company, Cerebras, which is building essentially wafer scale chips to tackle those requirements. But then machine learning is not special, in my opinion. There are many applications, some of which also use machine learning, and data is a performance energy bottleneck in these applications. If you look at the mobile end, applications are also bottlenecked by data. I'll give you some results from some of these applications later on today. Our systems are basically suffering, and they're going to suffer even more because we can generate more data in domains like this. This is genomics. Because of the success of device technologies in genomics, we're able to reduce the cost of sequencing genomes significantly, as you can see in this curve. And this is compared to the cost of a transistor reducing as dictated by Moore's law. So basically, we can actually, the cost of sequencing genomes is much lower than the cost of a transistor. If you think about this, we can generate much more data than we can put transistors on a chip. And I think we can make the easy conclusion that how are we going to process this data? I like genome analysis because it's an area that we do a lot of work on. Basically, the way I think of this is we have these devices that are extremely powerful, extremely good, and we want to reach scientific discovery and medical advancements. Unfortunately, we're bottlenecked by data and how fast we can analyze it. And there are clearly a lot of interesting things you can do once you can analyze genomes. I think COVID-19 showed us a very small fraction of this. This is a data generator. This is the Oxford Nanopore device over here, and it's a nice device, and it can generate data very well, but it's a very dumb device. It cannot do any processing. So if you want to do some processing based on the data that this generates, it's very cheap also. It's $1,000 or so. You need to move the data. You need to move the data to a laptop, but usually a laptop is not sufficient. You need to move the data to a data center, and you need to parallelize it. So we cause a lot of churn of data movement across our computing systems because we cannot process data locally. This is at the macro scale. And also at the micro scale. If you look at the micro scale, these devices are not able to process data, even though they're sensing data, they're generating data, and they're storing data. So this picture is very similar in many domains. I like this picture in genomics. So you can see another device over here that's specialized, very special purpose device for data generation. It's very fast, but then you move a lot of data to very slow devices that are not specialized for the task in general. And if you don't like genomics, pick video. Video analytics is very similar. Pick some other domain that you may be excited about. We can generate lots of data today. In a car, for example, there's video, there's a lot of data collection. World Wide Web is another example. You collect a lot of data. We have basically special purpose data generators everywhere. But our data analysis is general purpose, and a lot of data movement happens. Okay, genomics, I'm not going to talk more about, but this is a fascinating area, in my opinion. If you're interested, we've been writing papers about it, and it's an area that's not easy to get into, but I believe future is there. Let me give you some idea of what we can do with some devices today. Today, we have FPGAs. Today, we have FPGAs that have high bandwidth memory connections. Basically, FPGA can be coupled to very high bandwidth memory using HBM on a board that looks like this. And you can offload computation to this near memory reconfigurable logic, and you can configure that logic to be specialized for the application. And you can do this. We did this together with IBM, for example, for weather modeling, the Cosmo weather model, as well as genome analysis, alignment filtering in this particular case. And if you do that, you actually get a lot of performance and energy efficiency. So this is a step in the right direction, in my opinion. You can read the paper for more, but you need to do some effort, of course, to program this to get higher performance and higher energy efficiency at the same time. I will not go into a lot of detail. I'm going to talk about the future. I'm not going to talk about what you can do today. But that in the future, we need to be much more efficient, in my opinion. And the future is going to be a lot more embedded, in my view. You can see that the devices are getting actually smaller, but also more powerful in terms of data generation. Okay, we have a lot of courses on these topics. If you want to get into genomics, we're happy to help. And these courses are live streamed, by the way. We have some industry attendance too. So I give you one application domain, but there are many applications domains. In the end, the ability to generate data overwhelms our capabilities: storage and memory capability, communication capability, and in the end, computation capability. And we actually design very powerful processors today, but they're in the end waiting idle. They're not doing much compared to what they should be doing, in my opinion. I'm going to give you some more data points later. And data also greatly impacts robustness, energy, performance, and cost. If you look at the fundamentals, a computing system should consist of computation, communication, storage, and memory components. And we've decoupled them over time, and we've heavily optimized the computing. If you look at the history of computing, that computing unit has been optimized significantly, whereas we've kind of ignored the rest of the system. In the sense that the rest of the system cannot do anything active. You have to bring everything to the computing unit. Today, it consists of CPUs, GPUs, FPGAs, machine learning accelerators, video accelerators, specialized many accelerators, basically. But you have to bring the data all the way there. Everything else, which is essentially all of the computing system, to a first approximation, is doing nothing. Well, nothing other than storing and moving data. So this is my picture. It's an old picture, but it still stands today. If you look at the processing computing units, these are the cores. Everything else is there to store and move data. In a general purpose system, it's a caches, interconnects, other caches, other interconnects, other caches, other interconnects, memory controller, other interconnects, other caches, other interconnects, storage, other interconnects. Most of the system is dedicated to storing and moving data. If you do the calculation, it's actually more than 95% of the real estate of a single node. Now, looking at this system, if you show this picture to a child, they would probably think that, oh, you don't have a data problem. You're putting all of your resources there. Yet this system is still bottlenecked by memory. This should tell us something. Maybe we're doing something completely wrong. Of course, I'm a bit provocative, but if you don't like my picture, this is AMD's picture. It's a real picture. If you look at this box over here, it's L2 and L3 caches, just L2 and L3 caches. The rest of the chip is memory interconnects, other memory, other memory, other memory. So you see what I'm getting at. And then we're putting more and more caches. This is the 3D stack cache that AMD is putting, which is great from a technological perspective, but from a system perspective, are we really doing the right thing? And if you don't like AMD, there's IBM, and I could keep showing examples, but the picture is the same. This is my favorite example. This is a system on a chip. You can see Apple's two big chips over here connected somehow. This is a lot of SRAM, and then there's a lot of DRAM, and there's a darkness, which we call storage, which has really enabled these systems, in my opinion. Okay, so that's the picture. I'm going to give you some more results, but before I move on, I will say that we've done some studies together with Google on these 4 important workloads, and we found out more than 60% of the total system energy on these mobile workloads is spent on data movement, and we have not really exercised the system very badly, in my opinion. Later, we repeated some similar study using Google's edge machine learning models, and we found out more than 90% of the total system energy is spent on on memory in large machine learning models. These are LSTMs, long short-term memories, transformers, etc. So once your data set grows, the system energy that's spent on just moving the data around grows. So in the rest of this talk, I'll give you data-centric computing, but I should also lay out the vision we have. I think we need to build intelligent architectures going into the future. Why? Because they're going to make decisions for us. But I think these architectures also need to be fundamentally intelligent. Today, what we're doing with our architectures is, I would say, dumb. So what does this mean? How do you handle data well? We need to ensure that data doesn't overwhelm the components we design. We're going to talk a lot about this via intelligent algorithms, architectures, and system designs. This algorithm architecture device co-design in the end. But we also need to take advantage of the vast amounts of data and metadata flowing through the system. And this is something that I'm not going to talk about, but I think this is very important as well. When we're designing our systems today, when you're designing an architectural controller, for example, a memory controller, a cache, these don't make data-driven decisions. The decisions they make are human-driven, meaning the designer goes and puts some heuristics, and during runtime, these components make decisions based on the heuristics that the designer was able to imagine or evaluate, etc. They cannot learn from experience. This is very unintelligent in my view, in the sense that an intelligent agent needs to make experience-driven decisions. Humans, for example, right? We call ourselves intelligent. I interact with the environment, and based on the feedback from the environment, I change my actions. This is basic reinforcement learning. So in general, I think we need to have learning-based components in our design. That's lacking very much. And we need to actually really improve our processes to enable those learning-based components across the stack. And on top of this, I think this third dimension over here is today, data has a lot of properties. Data has security properties, privacy properties, approximability properties, error tolerance properties, even performance like locality properties, and you can keep adding to these. Unfortunately, those properties at the high level are not discovered even when they're discovered, they're not communicated to the underlying hardware. As a result, a hardware agent makes a decision based on not the characteristics of the data, but based on something else, components in general. I'll take the example of a memory controller again. When I design a memory controller, I have two requests, request A, request B. How do I make a decision in terms of which one to prioritize? Well, I look at which bank is not busy, which row is not open or open. These are all component-based decisions. They have nothing to do with data semantics. I cannot say, oh, this request is very security critical, because I don't know that information. And I cannot make a decision based on that security criticality property. So I think we need to really understand exploit properties of different data in making decisions in our systems. So this leads us to these three directions, in my opinion. I'm going to talk about the first one a lot today. We need to change our systems from processor-centric to data-centric. We need to change our systems from systems that are making designer-dictated decisions or designer-based heuristic-driven decisions to more data-driven, learning-based, experience-based decisions. And we need to change our systems from making component-based myopic decisions to more data characteristic-aware decisions. We call this data-centric, data-driven, data-aware, and we've written papers about it. If you're interested, I can talk more about the other two, but we're going to jump into the data-centric part. But I believe in all of these, we need to revisit the entire stack. Clearly, this is not going to happen overnight, but over time, in my opinion, by changing the paradigm slowly, we can get there. And I'll give you hopefully some examples from the data-centric part at least. So let's jump into the data-centric or memory-centric architectures part. I call this actually processing data where it makes sense or where it resides. If you look at a data-centric architecture, data is the king, if you will. Today, processor is the king. We should really change that mindset. If the data is the king, then we should probably be processing data where it resides or where it's generated. We should really enable low latency and low energy data access fundamentally, as opposed to being designing many levels of hierarchies that are not really fundamentally reducing the latency and energy. We need to make things more lower cost, storage, and especially, and then we need to manage data intelligently, especially many different properties of data. Again, I don't have time to talk about all of these. We're going to focus on the first one, but I'm going to motivate the first one in a different way as well. So I call this processing data where it makes sense. Then the question becomes, where does it make sense? My answer to this is everywhere. Everywhere data is generated and resides, we should be having processing capable. Sensors, storage, DRAM, caches, memory controllers, SRAM, register file, and then you get to the computing units today. This is not a new idea. There are papers that are written since 1960s. If you know of earlier papers, please let me know. These are beautiful papers. They introduced the idea of near memory processing, which is happening in a part of the industry right now. But there are more radical approaches also, like I will describe. And this is Harold Stone's paper. You may know the name. Okay, so this idea has been examined for, let's say, 5 decades, on and off, in different ways. Why is it interesting today? I would argue that we have nowhere to escape. The problem we're having with memory technology is pushing us to do intelligent things in memory, as opposed to treating memory as commodity, and memory is not intelligent at all. It cannot even handle its own problems. This is going to change. It's already changing, actually. And the second part is applications, our systems, and our requirements are pulling us to do something different, have some more intelligence on the memory side. So I'm going to quickly talk about the first one and then talk about the second one a little bit more. I will say that designs are squeezed in the middle today. Basically, today, memory technology scaling is not going well. Over the course of 60 years, actually 50 years, DRAM, for example, scaled very well, but today we're having a lot of problems. And these require intelligence on the memory side to fix. And then on the application and system side, we have a lot of bottlenecks, data access, energy, and power, and data moment energy dominates computation energy. And our requirements have changed also. In the past, we said performance, and then power came, and then we had performance power trade-offs. Today, we talk about sustainability. Today, we talk about not a performance power trade-off. I want performance and energy efficiency, energy at the same time. I want to improve both, basically. We're greedy at this point. We cannot go back, let's say. So I believe that we can improve all metrics by minimizing data moments. So we're squeezed in the middle, I will say. As a result, things are happening in industry that has been extremely conservative, if you will, memory industry I'm referring to. So people are adding 3D stacking, for example. You have a logic layer under memory layers, and you can put processing units there. Micron has been experimenting with things unsuccessfully. More recently, there are companies that have been developing general purpose processors inside DRAM. These are DRAM chips that are modified. Samsung has introduced their DRAM chip that's modified, SK Hynix, Samsung and Meta, and Alibaba has been producing their DRAM chips also. We're going to get back to this. And there are many, many other experimental chips and startups. So if I actually was giving this talk in 2018, the bottom part wouldn't have existed. Okay, so why is this happening? I think I'm going to motivate it through technology very quickly. Basically, we are having a lot of technology scaling issues. I won't bore you with a lot of details over here, but technology scaling is not going well in DRAM. Because as you make the cells denser and denser, as you put more cells in a DRAM chip, it becomes unreliable. There's a lot of noise in the DRAM chip. And this is a study that we did with Facebook across many machines, all of the data centers that Facebook uses. This shows a correlation between the DRAM chip density that's employed in the server. This is a production data center server, and this is server failure rate. Clearly, denser chips lead to more system level failures. And we did a lot of work actually to understand these issues. We built FPGA-based memory controllers to test memory. I'd be happy to talk about them. I don't have a lot of time to describe these things. We've open sourced this. Other people are using these systems. These are real systems that we have pictures of, clearly. And we found out together with Intel that you can predictably induce errors in most DRAM memory chips. This is one example of the technology scaling problem. I think it's one of the worst examples. This is called the RowHammer problem. I'm just going to give you the idea of the problem. Basically, this is a read disturbance problem. If you want to read memory, DRAM, you need to open a row, activate a row, which means apply high voltage to the word line. If you want to read something else, you need to close that row, apply low voltage to that word line. Now, if you keep doing this repeatedly, open, close, open, close, open, close, open, close, activate, precharge in DRAM, it turns out nearby cells get bit flips. Now, clearly, this should not happen. You should not disturb anything when you're reading memory. But now you're disturbing some cells that belong to some other applications, potentially. And some also, it could be your application, right? You could get silent data corruption, essentially. We call this the hammered row. We call these the victim rows. And we showed essentially, at the time, this is 2012, that more than 80% of the chips manufactured by the 3 major DRAM manufacturers of the world are vulnerable to this effect. Today, those numbers are all 100%. Fundamentally, devices are vulnerable because cells are getting closer to each other, and this disturbance is very difficult to prevent unless you move to much more expensive materials, if you will. As a result, DRAM manufacturers are introducing, as I will show you, intelligent DRAM, if you will, slightly intelligent DRAM. So basically, this could be a system security vulnerability as well, because those bit flips, some hacker can actually use those bit flips to circumvent memory isolation. It could circumvent all of the virtual memory protection mechanism that you may be putting to your systems. And as a result, people are writing articles like this. Forget software. Now hackers are exploiting physics. I like this one. I prefer physics to software, frankly, also based on my background, if you will. Okay, so basically memory scaling issues are real. There have been a lot of papers written about it, and we still keep writing papers because it's getting worse. Cells are becoming smaller, not larger, and they're getting packed more and more. If you're interested, you can learn more about this from our tutorials. And if you really have only 20 minutes, it's a 20-minute version, but it's not up to date, as you can see. So how do you solve this problem? Well, actually, I think the solution is really intelligent controllers, like we do in flash memory SSDs, except flash memory is far away, so you could actually have a lot of slack to do it. But you need to do it in DRAM, and increasingly, I believe, you need to do it in SRAM and other memory technologies as well. Now, I'll tell you quickly what the memory manufacturers are doing. Finally, they're acknowledging the issue. This is ISSCC this year. A paper from SK Hynix basically says that, describes how they not solve, but mitigate the RowHammer problem. And I like this paper because they actually credit us because their solution is very similar to the solutions that we have proposed in the past. And they actually modify the DRAM chip. There's slight intelligence. There's some amount of intelligence to detect this RowHammer issue inside the DRAM chip. It's not just Hynix. Samsung also released an archive paper where they talk about this also, as you can see. This is much harder to read if you're interested in reading. So you can say, okay, other memory technologies. Unfortunately, all of the other memory technologies require intelligent controllers as well. These memory technologies are not perfect, even in some cases, much worse than DRAM, like in endurance cases, for example. As a result, they also require intelligent memory control. So I think we have nowhere to escape. I could keep giving you more and more reasons in terms of why memory technology requires more intelligence, like hybrid memories, heterogeneous memories is another example. But we don't have time, so we should really move to the next part of the talk. So we need intelligent memory control, and it's already happening. Okay, let's look at the system and application side. This is actually worse, I would say. Even if the first one wasn't happening, which it is, I believe this alone should motivate us to do something different. Basically, we're having a lot of problems with data access. And I think I will motivate this in a modern way, if you will. I think we want a future that looks much nicer for future generations than a future where computing is really destroying the world because of its power requirements. And I think that we will get there. We'll have billions of devices. Data centers are already actually destroying part of our environment. The question is, what do we want? I think we want energy efficiency, sustainability, but we also want high performance. We cannot give that up, in my opinion, because we have a lot of issues to solve. So I think to get there, we really need to realize what's the problem. I believe the problem is data access and how we treat the data access today. Our current design principles are exacerbating the data access and making our system much worse. Data access fundamentally consumes energy. Data access fundamentally consumes performance because you need to move the data, right? That's energy inefficient, performance inefficient. We keep making things consume energy because we keep moving the data. We try to overcome the performance loss, mostly unsuccessfully, as we will see, because we make our systems a lot more complicated. What do? We add hierarchies of memory, right? We add prefetchers. We had many levels of multi-threading. We add out-of-order execution. Basically, our systems are humongous machines to tolerate this data access, yet they're still not doing well. So I will also say that even though we build these humongous machines that try to tolerate data access, in many applications today, they're very inefficient. They don't work. These mechanisms actually don't work. And people show that. If you take a random access application, most of these mechanisms are useless. So really wasting a lot more energy by adding more complexity to our systems. We're in this vicious cycle where energy is compounding. Okay, so I think if you're in a vicious cycle, it's always good to pinpoint what's the fundamental problem. Basically, we're processing data far away from the data. And we need to change that. So I showed you this picture before. Computing unit is the king. We're processor-centric. And this comes at great system cost. Yet we know the problem. So I'm going to give you some more data from others right now. This is 1996. Dick Seitz, who was the chief architect of Alpha processors at the time. After they finished a flagship Alpha processor, he basically writes this one-page article saying it's the memory stupid. And basically, he says that we designed this processor. It's this flagship state-of-the-art. It's able to finish 4 instructions for Alpha instructions at the time per cycle. But unfortunately, on this important database workload, it's finishing 1 instruction every 4.7 cycles. So it's operating at less than 5% of its peak bandwidth. Why? It's waiting for data to come back from memory. And he ends this article with this sentence. I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. Only is his emphasis over there. I mean, I agree with him clearly. That's why I'm talking to you. But I believe that we need to do more. So this is my own PhD thesis. Together with Intel, we actually did something similar to what he described 10 years later. And on all of the workloads that Intel used to design their flagship processors with, we found out that most of the time the processor is waiting for data. Okay, and you can read the paper that resulted in it. This is data from Google, which shows the same thing. This is 2015. According to Google, this is all of their data center workloads. And on a flagship processor at the time, state of the art, the processor is waiting for data most of the time. It's actually finishing instructions only 10 to 20% of the time. Okay, so even though we're dedicating almost all of our resources to data storage and movement. So that was performance. You can say, okay, maybe I'll live with it. Let's take a look at energy. Energy is actually even worse. This is data from Bill Daly, High Peak 2015. You can argue these numbers right now, but the orders of magnitude is similar. So a 64-bit double precision floating point operation, 20 picojoules. A DRAM read or write, 16 nanojoules. That's 800x difference. Okay, maybe you find 800x large, I agree. It's closer to 150x. Fine, that's still large. Now, imagine doing an addition, floating point addition. Does it really make sense to bring the data 2 pieces of elements to the processor and then write the data back with one more memory access? That's 3 times 800x or 3 times 150x. Now imagine what kind of caching locality you need to have to overcome that energy cost. It's a lot. So basically, this is why our caches are not efficient. Okay, that was an expensive arithmetic operation. What about a cheap one? This is an add, a 32-bit add. It's not the cheapest add, clearly. And the difference, according to, again, Bill Daly's later numbers, the difference is 6400x compared to a DRAM access. So that's even harder to overcome. Okay, as a result, we see on real workloads that are not actually very, very intensive, you see 60% of this total system energy spent on data movement. And in some more intensive workloads, more than 90%, actually more than 99% of the total system energy spent on memory. So I will argue that we do not want to move data. We need a paradigm shift to enable computation with minimal data movement. We should compute where it makes sense. Sometimes it makes sense to actually compute in the processor.
but most of the time it doesn't. So we should really enable computation capability across the entire system. And we should make computing architectures more data-centric. So this brings us to processing inside memory, but I'm going to focus mainly on main memory today, maybe talk about storage a little bit also. But this idea needs to be applied everywhere where data resides, including inside the processor chip where you have a cache. Today, there's a decoupling between processor and cache. You still need to bring the data from this huge cache to the processor, right? Why not actually process the data in parallel inside the cache? That may be easier to actually accomplish within your own domain if you're designing a chip. But I'm going to talk about main memory, which is actually much bigger. And in main memory, you can actually store a lot of interesting things. Today, people store things so that they don't go to storage, but they still go in some applications. Basically, we would like to ask questions to memory. Memory, can you process this data? And the memory says, yes, here are the results. That sounds good. Of course, it's easier said than done. There are many questions over here. How do you design the compute-capable memory and the controllers, processors and communication units, software and hardware interface to enable that? How do we design the system software compilers and languages to make this easy and effective? And how do we rethink the algorithms to match the computation capability in the memory devices that we have, and vice versa, actually? So I think this is really an across the stack design problem. I will also mention that there's theoretical foundations we really need to rethink. Because if you look at computing theory, if you've taken a computing theory course, algorithmic complexity course, you count operations, right? Big O notation, big theta notation. That's all compute-centric. We don't have a data-centric theory of computing because we have not had data-centric systems. We need to build that data-centric theory going into the future. Okay, so there's a lot to talk about over here, and clearly we don't have a whole lot of time, so I'm going to give you some examples, but I should also mention that we have a processing in memory course. If you want to learn more, there's a lot. And we also hold tutorials at conferences. It's all online. It's all on YouTube. You can find it. You can actually watch it at your convenience. We have an upcoming tutorial at the ISCA conference also. I should also say we need to think differently from past approaches to make this successful. Now I'm going to give you some mechanisms and examples of this. But before that, let me define some terminology. So the terminology in processing in memory, I call processing in memory in general as everything is encompassed by processing in memory. But I believe there are only two types of this, fundamentally. So let me define this. You have processor today, memory today, and we discussed that they're far away from each other, right? Processing near memory is the shorter term, in my opinion. Processing using memory is the longer term because it's analog computation. I believe we need to combine both of them in the end. So processor, memory. Processing near memory says, get the processor, logic units, do logic as you do logic today, but get them closer and closer and closer. Get them inside the memory chip, inside the memory controller, wherever basically. But processing and memory are still separate, but they could be very close to each other, clearly. And this is already happening in the chips that I've shown you. That's why this is shorter term. It's easier to program. It's fundamentally von Neumann model. But I believe it should happen because you're getting things closer. In the 3D stacking case, for example, processing and memory will be very close to each other. Now, processing using memory is processor, memory. Forget about the processor. It doesn't exist. What can you do with memory? This memory is interesting because any type of memory has analog operational characteristics that can be used for computation. And I'm going to show you examples from DRAM, but people are also showing this examples in RRAM and other types of memory. Any type of memory, if you look at the analog operational characteristics, analog curves, if you imagine it a little bit more, you can do data movement and you can do computation in it. Now, this is fundamentally different because you're exploiting analog operational characteristics. You're not adding any logic in the ideal case, of course. You may be changing the outside peripheral structures to enable this operation. So I'm going to talk about that first because I think that's the future. That's harder to enable going into the future. And then if you have time, we're going to talk about processing near memory. So in both of these, I'm not going to be, let's say, extremely radical. I'm still going to treat memory as an accelerator. The CPU will offload some operations and memory will do those operations. I think in the future, we need to change this model, be even more radical. Basically, all of these agents that can compute should be distributed. So it should be really a world for distributed computing people, let's say. But still, we're CPU-centric, let's say. Even this is harder, let's say. Okay, I'm going to also cheat initially. I'm going to not talk about computation. I'm going to talk about data copy and initialization. If you look at data copy and initialization, it's used in many applications. And if you imagine initializing a 16 terabyte database, you basically write zeros. And that takes time and energy. And Google, in fact, in the paper that I mentioned earlier, showed that in all of their data center workloads, approximately 5% of the total execution time is spent on these two function calls. It's amazing to me that only two function calls account for 5% of the entire cycles. Okay, clearly we do a lot of data copy initialization. How do we do it today? Because we're processor-centric, we move the data to the processor and then copy the data back to memory. Now, does this make sense? Again, show this picture to a 5-year-old or 10-year-old. They will say, oh, why don't you do it in memory? And that's the idea, basically. It's not rocket science, if you will, but I believe we should probably do this exercise with 10-year-olds. Maybe we need to really start from scratch in designing our computers. Okay, so if you look at that, this is low latency. I'm going to show you real numbers. This is low bandwidth utilization. We don't waste memory bandwidth on, let's say, not so important data movement operations. There are other data movement operations. We have to move the data potentially. No cache pollution, but you could eliminate that today. No unwanted data movement on the bus, basically. Basically, I'm going to show you a mechanism which reduces the 4 kilobyte page copy latency from about 1,000 nanoseconds to 90 nanoseconds unoptimized, and 3.6 microjoules to 0.04 microjoules. And the idea is very simple. This is the best case, of course. If you look at DRAM, it consists of a bunch of rows. This is the DRAM subarray. And then you need to amplify the data in the row when you read the data. That's the row buffer, sense amplifiers. Now we're going to take advantage of the row buffer and the chart sharing principles of DRAM. We first activate the source row, which brings the data into the row buffer. And then we activate the destination row, which disconnects the source row from the sense amplifiers, but connects the sense amplifiers to the destination row. And that way we can actually copy the data from the row buffer into the destination row. Basically, we use the row buffer as an intermediate place to copy data from one row to another. And this essentially accelerates your page copies. And the idea is 2 consecutive activates. It's negligible hardware cost. And you get significant latency improvements and energy improvements. So you can say that, okay, what about if the data is not in the same subarray? Yes, you need to handle that, and we have mechanisms to handle that. It's an old picture, but these mechanisms actually improve. Oh, something happened. These mechanisms improve performance, not as good as what I just described, but close enough, let's say. Okay. So this actually is so little hardware cost that if you go and abuse the timings in your memory controller, violate the timings, you can get close to 2 consecutive activates. And in real DRAM chips, this happens. Basically, by violating the timings in your memory controller, you can do this row copy very reliably. Most of the rows actually are very reliable. You can do that. This is fascinating to me. DRAM chips are clearly not designed for this. It's not documented behavior, but you can get very reliable row copy operation in DRAM chips. That's the paper that introduced it. We built on their idea. We basically designed an FPGA-based framework that does this. And you can download it. You can actually look at system-level approaches to take advantage of it. We have end-to-end analysis of this row clone, as well as true random number generation, which I'm going to briefly talk about. Okay, and this is our system. We're happy to support it. And we see real results, real application-level improvements in row copy and initialization. Initialization is a special case of row copy. That's why I'm not talking about that. Okay, so there's a lot more to talk about, but I don't have time. Let me talk about computation. This also happens in real DRAM chips. Harder. You need to violate the timing parameters much more carefully, but you can actually get in DRAM and or and majority operations in real DRAM chips today, even though DRAM chips are not designed to explicitly support it. Let's take a look at how that happens. Basically, you're going to use analog computation capability in DRAM again. And the idea is activating multiple rows, in particular 3 rows, concurrently performs computation. And we get significant performance energy improvements as discussed in this paper. I believe new memory technologies, which I'm not going to talk about today, enable even more opportunities, but these are longer term because new memory technology has a lot of other issues to solve. But I believe they're fundamentally more efficient because DRAM reads are destructive. In new emerging memory technologies, they're non-volatile, they're not destructive, so you can actually operate with minimal data movement. They also enable matrix vector multiplication due to crossbar array operations, which I'm not going to also talk about. I'm going to flash one slide so that you can look at the papers if you're interested. Let me talk about DRAM. So I'm interested in DRAM because DRAM is all the main memory today, right? So how can you do AND and OR in DRAM? I'm showing you 3 DRAM rows over here, only one cell, but imagine a row being 8 kilobytes. And then imagine doing this across all 8 kilobytes of data. And then imagine potentially doing this on thousands of subarrays in DRAM. So you can do this in millions of bits at a given point. We're going to do bit operations. So if you concurrently activate these 3 rows, apply high voltage to the word lines, what happens is all of these 3 rows get connected to the bit line. And if at least 2 cells are charged, you get the charge state at the end. If at least 2 cells are discharged, you get the discharge state at the end in an ideal circuit. Basically, this is a bitwise majority function. So you can do bitwise majority across millions of bits in DRAM in one cycle. Now, this is nice. You can rewrite this if you set C to 1, you get the OR of A and B. If you set C to 0, you get the AND of A and B, bitwise AND, bitwise OR. You can say, oh, I don't have NOT, so I'm not functionally complete, but you do actually have NOT. This requires changes to DRAM. These operations can be done by violating the timing parameters if you're extremely careful, but not if you look at the inverse. I don't know, I cannot find my thing over here, but if you, maybe I'll just go over here. If you look over here, this is the charts. This is the value. If you activate one row, this is the value of the row is here, and the complement is on the other side of the sense amplifier. You just need to move it somewhere else. So this requires some changes, and that's what we do in the paper. But now you're functionally complete. You have majority and not, that's functionally complete. You can actually, rethinking your algorithms, you can do everything using this. And I'm going to talk about that in a moment. But some algorithms are better fits. People already use block bitwise operations nicely, in databases especially, and also web search. These are real workloads that do block bitwise operations. And we actually tested our system in simulation using the database that's designed for block bitwise operations. And we see significant end-to-end performance improvements, 4 to 12x. Now you can say that that's not easy to program. I absolutely agree. You need to put the effort to actually do this. But GPUs were not easy to program 25 years ago also. Okay, now we want to make it easy to program. And that's why we introduced some frameworks to enable this bit serial processing. I'll just give you the basic idea. Essentially, user can specify any operation using AND or NOT logic. Do we have any clicker? Not the clicker, but just the yeah, laser pointer. Maybe that's mine, but it doesn't work because somehow I missed the. Anyway, yeah. Once you have it, I'll take it. So basically, you can specify any operation over here, AND or NOT logic. It could be convolution, it could be matrix multiplication, it could be whatever you think of. Basically, as long as thank you very much. As long as you specify it using this AND or NOT logic, which we know very well to do in EDA for sure. Basically, we convert it to majority inverter logic, and then using design optimization tools, we optimize this, and then we convert that to a micro program of DRAM commands, essentially triple row activation, a row clone, and we do allocation of rows in DRAM, etc., which I'm not going to go into. But you have a micro program associated with an instruction. It could be convolution, it could be matrix multiplication. It could be whatever, it could be even larger, right? So this could be anything in the end. And then when an application uses that operation, using this bulk bitwise operation, it gets invoked in the memory controller, and the memory controller executes this micro program to actually finish that operation. And that's the idea. This way we generalize the idea, and as a result, we see significant throughput and energy efficiency improvements compared to CPUs and GPUs. And you can see that the energy efficiency improvements are much larger than the throughput improvements, although throughput improvements are actually quite good as well. Okay, so we're actually trying to make this even more programmable. We have some works that I'm happy to talk about separately, and there are actually people who are building compilers for this purpose. Now, some operations are harder to do, so you need to actually do more intrusive things in DRAM, and this is where lookup tables come in, and we introduce lookup table-based execution, which I'm not going to talk about here. What else can you do in DRAM? You can actually, by abusing DRAM, if you will, or by understanding what DRAM can do by violating the timing parameters, you can do a lot of things. In this work, for example, we show that by violating the timing parameters, when you access a row, you figure out that some cells in DRAM always fail, meaning they form a signature of the device. This is essentially a physical unclonable function. This could be very useful for remote attestation of the device. Now, similarly, when you violate the timing parameters in a given row, whenever you access it, some cells fail randomly. In this access, they fail. In this access, they don't fail. And you figure out which cells fail with 50% probability. And this is a true random number generator in DRAM. There are actually fascinating ways of doing true random number generators in DRAM. I don't have time to talk about it. And we have end-to-end mechanisms for this. We actually released how you can do this in this FPGA-based infrastructure that I mentioned earlier. But there are better ways. So why is this interesting? This is interesting because this shows that DRAM actually can do a lot of interesting things that are expensive on CPUs today. We actually have specialized structures for this. But once we move computation to DRAM, we need these security functions going into the future. So DRAM is special, but not as special because any memory can do computation. And we actually have a lot of work on flash memory. Flash memory can do something similar. I don't have time to talk about it, but the idea is basically very, very similar. This animation shows the idea. In Flash, you can do this up to 48 rows. Up to 48 pages, you can do a 48 input 48 input AND operation. OR is hard. And in Flash, fundamentally, you can have an inversion. So you can actually do essentially the same thing that we described in Flash memory as well. So I can say, okay, what about other technologies? Other technologies can actually do this. There are papers that are written on, about it. Other technologies can actually do more. If you have the crossbar array structure, you can create matrix vector multiplication, but I don't have time to talk about those today. Okay. So if you have time, I'm going to jump into processing near memory. Wolf, if you give me guidance, otherwise I can skip it and then conclude also.
If we want to leave it, then maybe 5 minutes, before 5 minutes.
Total? Okay, 10 minutes. Okay. Okay, yeah, I'll go through very quickly, basically. So processing near memory is easier to do. You can basically put logic near memory. And here, I think the interesting thing is what kind of applications will benefit. We look at a lot of graph processing. And for example, if you have 3D stacking of logic and memory, you can put logic underneath memory and you can customize it. And that's what we did essentially. We don't have time. I'm not going to go through this, but this is what I consider like a GPU-based accelerator. And the idea is to have a distributed connection of these 3D cubes, and then partition your graph on top of it. And then whenever you update a graph node, you send a message to the processor that's housing that graph node. Meaning you don't move the data, you move the function to the data. So it's remote function-based programming. And internally in the logic layer, you do also that, essentially. And the idea is to minimize the data moment as much as possible. Okay, I don't have time to talk about this, but this system is, you can see that it's very different from today's systems. Today's systems have the processor and memory dichotomy. In a near memory processing system, memory and processor are coupled, and then you can have a distributed system of those. As a result, you can enable much higher bandwidth to the processors themselves. And you get significant performance improvements on the graph workloads and significant energy improvements also. This is old work. We did this around 2013, actually. Later works improved. And we're closer to 2 orders of magnitude energy reduction and 2 orders of magnitude performance improvements. Okay, I'm going to skip some of these, sorry, since we don't have a lot of time. As I said, I have a lot of slides. Okay, something is happening here. So I want to go to something toward the end. Sorry. Yeah. This one. So, okay, how do we enable this? Clearly, you can design any hardware. Let me remove this also. But enabling it is the hard part. I believe we need to do a lot of work. So, and most of these are software and system level issues. Application of software, ease of programming, how do we provide the system and security support, runtime and compilation systems, and infrastructures. But I believe more than anything else, we need to change the mindset, because every single thing that we do in our systems today is a result of the compute-centric mindset. Data mapping, data allocation, everything basically. If you don't change that mindset, you will not move anywhere, if you will. And I've seen this with reviewers also. Okay, so I will, again, skip these. These are interesting things, but let me talk about processing in memory in the real world for a couple of minutes, and then I'm going to conclude. So today, things are happening. Industry is moving in some direction. There are a lot of, actually, if you go to ISSCC and CICC, you'll see a lot of emerging memory technology-based papers, but also there are things that are happening. And if you're interested, we have these tutorials that talk about some of these things. Let me talk about a couple of examples. This is the UpMem processing in DRAM engine. These folks basically put a processor inside the DRAM, and a big processor, a hefty processor, actually. These are real. We actually experiment with them. We write papers about them. But this is what the processor looks like. It's a multi-threaded processor. It has its own downsides, etc. For example, it cannot do more than 8-bit multiplies. Okay, but there is a processor inside DRAM, and you can experiment with it. And some workloads benefit greatly. Let me give you an example over here again. So there are some workloads that you can write. They benefit greatly. There are some workloads that don't benefit greatly because of the lack of, let's say, a good multiplier inside the DRAM and some other design choices that they're made that require a lot of communication between the processor and DRAM. Is it the ideal system? This is not the ideal system, but this is a system you can experiment with and see what you can do. And again, we have a lot of materials, including benchmarks that we have developed for this system. Let me also give you a couple of other examples over here. You can do machine learning training. So there's a lot of workloads that you can do over here. Again, I'll refer you to the papers, and these slides are available for you if you're interested. Samsung is putting functions in memory, and this is essentially for machine learning. They actually have floating point multiply, which UpMem lacks. This is very specialized as opposed to general purpose like UpMem, mainly for machine learning workloads. And they advertise it. They have some papers that describe its performance benefits, etc. Samsung and Facebook together designed this large module where they have a buffer that can do processing for recommendation systems, which is interesting. Clearly, they have papers about it. SK Hynix has designed this GDDR-based system, which is essentially accelerating machine learning workloads also, except it's a DRAM chip. So all of these are DRAM-based. People are modifying DRAM today, which was a taboo, let's say 10 years ago, if you will. And if you're interested, they actually talk about it publicly also. This is from our RealPIM tutorial. We invited them to give a talk. Okay, Alibaba is designing their own systems, their DRAM chips for recommendation systems as well. Okay, so there's movement basically. And I think more chips will enable this movement even more. So I'm going to skip these also because we don't have time, but I will, I'm about to conclude. Basically, I think we want fundamentally high performance systems that require data centric systems, and also fundamentally energy efficient systems that also requires data centric. I believe fundamentally secure also requires data centric, but I cannot prove that right now, maybe in 10 years. Okay, so let me conclude. I think we need our systems to be balanced. When I talk about digital design and computer architecture to the 600 student class at ETH, I say balanced system design is a very important design principle. And then I'm ashamed to teach them the compute-centric system today, because it violates that balanced system design principle immediately, right? So we're violating a very fundamental principle in our systems. Okay, I think to get back to more principled designs, which are better in other ways also, which I hopefully have shown you, we need to enable computation capable inside and close to memory. This can lead to orders of magnitude improvements, enable new application and computing platforms, enable better understanding of nature, which I don't have time to talk about also. And who knows what else. I think the future is bright, but we really need to do the research, design, which is really the really hard work across the computing stacks. As I mentioned earlier, people did the hard work for GPUs over the course of 25 years or so. I think we're just getting started with memory-centric computing. And if you look at this compute device, I think it's really, this also is another example of how we're violating the principles, if you will. This is where here, computation, communication, and storage, as far as we know, is quite coupled. Okay, let me actually finish. Let me thank people who have sponsored this work and other works. And most importantly, I'll thank my group who have done these works. If you're interested, you can learn more about them in these places. And we open source everything, almost everything we do, and you can find that information on our GitHub. I will stop with this slide. I'm happy to take any questions. Thank you.
Onur, thanks a lot. So I guess if the term tour de force applies, it's really to your wonderful, inspiring presentation. Hey, we have microphones here. Yeah.
Let's come back to the physics.
Okay.
Do you really think that the RowHammer is the main impact to the bit errors? What is about the PDN system when a stable voltage supply system? What we found is if you are not in the right impedance range of that PDN system, you receive a lot of bit errors. And these are not computable and predictable because it's dependent on the state, what you are doing in the system.
Yeah.
Question?
Yeah, so no, I'm not suggesting that RowHammer is the worst reliability issue. I think that was an example reliability issue, but I think there are many, many others. So I agree with that. There are other reliability issues. In fact, we covered some of those in our earlier papers. With Facebook, for example, we found out some of the impedance issues that you mentioned. Yeah, no question about that. I think we need to solve all of these reliability issues to make the systems better. Some things are more possible to solve with more intelligence, but some things are more possible to solve with ECC, for example, more randomized errors. I will also argue that better handling of the ECC, better understanding of the errors, better signal processing that you do in the system is also pointing toward more intelligence on that side.
Yeah, the other question is how we can solve this. Should we not design the memory in combination with the power delivery system?
Yeah.
Not separately? Why? The integrated circuit guys say to the customers below 2 milliohms or the range of 1 gig, everything is solved. But you cannot reach 2 milliohms.
Yeah, I mean, we should probably take this offline because it's a longer discussion, but yeah. I think, yes, we need to, in my opinion, this is also an example of memory being commodity, right? People think of memory as commodity. As a result, you don't do much effort on that end to design this to be much better. But we need to actually design it to be much better. I absolutely agree.
I need one extra hour.
Great. Yeah. So, further questions? Okay, maybe let me ask one. You gave some list of, I think it was slide 186, list of potential elements, and then you said change the mindset.
Yes.
That's the most important one.
Let's see if we can go back. Yes.
Yeah. What do you think? How will you? How can you achieve changing the mindset? How will you incentivize people?
Yeah.
It's applications and software. There's a lot of legacy out there, and people want to reuse that.
Yeah, absolutely. I think. I think how do you really change the mindset of the masses? I think it comes with examples, right? Initially, like what happened with GPUs, right? Some enthusiasts discovered that, oh, there's this hardware lying in almost all of our machines. Can we actually use it to do something big for our purposes? And a lot of people gave examples and examples and examples. And over time, companies also started jumping in and capitalizing on it. So it could happen that way. I think that's why we do a lot of these studies, and other people are doing a lot of these studies to show the benefits of this. So I think that's part of it. Education is another part of it, because immediately when we start educating students, it's like it's almost like set in stone, right? This computer-centric processor and memory. We don't even talk about it. In my courses, for example, I talk about processing in memory, saying that, oh, this is some other paradigm. I think we need to do more and more of that with future generations also, so that things don't get ingrained. But it's not easy, right? It's in the end, people need to see the benefits, and if the benefits need to be, let's say, if people want instant gratification, it may not be easy to obtain. I would say it's more of a long-term approach.
And perhaps a little bit related question. You talked a lot about DRAM, for example, or SRAM. There's also people are working on novel memory architectures. Later today, we'll have a talk on using RAM, for example. And then there's research on FerroRAM, of course, chips and so on. Will that? Do you have any idea on how potential novel memory devices, which might move into industrial usage, how will that affect? Will that make the option of processing in memory or near memory easier, or?
Yeah, I mean, certainly they have characteristics that enable some of these analog operations nicely, right? The matrix vector multiplication, for example, a lot of those memories have that cross-bar array structure. So I think the benefits can be even higher than that we see in DRAM and flash. Now, of course, the downside is these are, so there are downsides and upsides. The downside is they have other issues in terms of manufacturing and in terms of making things work. So they need to be viable to begin with. But this is also an upside potentially, because you can integrate the processing mechanisms early on while they're being designed. So have a more complete solution for processing. So I think maybe a better way to, let's say, get these technologies more better adopted would be selling them as computing devices as opposed to just memories. So I believe there's an opportunity there. But of course, it's not easy also, right? Yeah.
Okay, thanks a lot. I hope you'll still be around.
I'll be around, yeah. I'll be around today. Yeah.
So pretty sure there will be more one-on-one interaction during the coffee break and potentially during dinner tonight. So, thanks
Thank you
again for your wonderful wide-ranging presentation here.
Thank you very much.